What's up, everyone? This is our second video for solving trigonometric equations. And in this video, we're going to be looking at four equations where the argument of the equation is more complex than the ones that we looked at in the previous video, okay? So first equation here, sine of 2 theta is equal to 1/2. We're solving it for the interval 0 to 360 degrees, okay? Now, the argument of this equation is 2 theta, all right? And think back to when we graphed trigonometric functions. If I were graphing y equals sine of 2 theta, that 2 is going to have a horizontal stretching effect on the parent function to where it's going to give you 2 cycles over the interval 0 to 360 degrees. Recall the normal period of the sine function is 360, but if we divide it by that b value of 2 that's within that argument, we end up with 180 degrees for the period. So that means you're seeing 2 cycles of the function over the interval that we're trying to solve for, which ultimately allows for more solutions, okay? So here's how I want you to approach this, all right? Whenever that argument of the equation is something other than theta or other than x, I want you to ignore it to start, okay? So we're first going to begin by solving the basic equation sine of x equals 1/2, okay? So we're treating 2 theta like x right now, right? So the thought process here is that x has to be an angle that's in quadrant 1 or quadrant 2 where sine is positive, okay? Drawing this out, y would be 1, r would be 2, there's radical 3. So this value for x could either be 30 degrees for quadrant 1, or if you brought it into the second quadrant, 150 degrees, okay? All right, now we bring back into account that we're not really solving for x here, we're solving for 2 theta, okay? So x is the same as 2 theta here. That means 2 theta should be equivalent to 30 degrees, and it should also be equivalent to 150 degrees, right? That means theta could really be 15 degrees, or it could be 75 degrees. So right there are 2 solutions, okay? And those are the solutions over the first cycle of the curve, all right? Now, consider the fact that the function is periodic and that there's really multiple places where we're equal to 1/2, right? So normally we're equal at 30 degrees. Well, a coterminal angle to that would be 360 degrees later at 390, right? So I'm going to solve a third little equation here. I'm going to say that 2 theta is equal to our original 30 degrees plus 360 degrees, or 2 theta is equal to 390, right? 390 is that coterminal angle to our original 30. Solving for theta here, I end up with 195 degrees, which is still within the interval that I'm trying to solve over, okay? And I'll do this also with the 150 degree angle. I'll add 360 to it to give me a coterminal angle of 510. Dividing by 2 takes me to 255, which is also within the interval 0 to 360 that I'm trying to solve for. Okay, so notice I end up with 4 solutions to this equation over the interval 0 to 360. Okay, you can verify this graphically. Okay, notice I have the curves y equals sine of 2 theta and y equals 1/2, and there are 4 intersection points between 0 and 360 degrees. The x coordinates of those intersection points are the solutions that I came up with: 15, 75, 195, and 255 degrees. Okay. All right, next example. Here, the argument of the equation is theta over 2. Theta over 2. So my b value in this case is 1/2. So the normal period, and I should have back up here. Notice we're trying to solve for 0 to 2 pi now. So we're in radians, okay? So normal period when we're in radians is 2 pi. If I divide that by this b value from the argument of 1/2, that gives me 4 pi. So you're only seeing half of one cycle or half of one period over the interval that we're trying to solve for, 0 to 2 pi. That means we'll probably have less solutions than we did in the last example, okay? So we'll begin the same way that we did the previous problem. I'll treat theta over 2 as though it's x. All right, so for a moment, I'm solving the basic equation sine of x equals 1/2, which of course we already did that in the last problem, but now we need it in terms of radians. So instead of 30 degrees, I'm going to say pi over 6, and instead of 150 degrees, I'm going to say 5 pi over 6, okay? Now we take into account that x really represents theta over 2 for our actual equation we're solving. So I'm going to take theta over 2, set that equal to pi over 6, and I'm also going to set it equal to 5 pi over 6. All right, so solving for theta would require you to multiply both sides by 2 for each of these. And that's going to lead me to theta equaling pi over 3. Or theta equaling 5 pi over 3. Now both of those are in the interval 0 to 2 pi, so I should be okay keeping those. All right, now understand if you were to try to go an extra revolution and get a coterminal angle to pi over 6, you'd have to add 2 pi to it, right? That's going to lead me to a coterminal angle of 13 pi over 6. And if I solve for theta here, multiply both sides by 2, theta is going to end up being 13 pi over 3, which, while it's a solution to the equation, it's not a solution in the interval from 0 to 2 pi. So I'm not going to include that in my solution set. Okay. Now let's verify all this with Desmos. All right, so in my settings, I'll change the, well, I'm in radians, okay, and I'll change the x-axis to go from 0 to 2 pi, the interval I'm trying to solve over. And I'm going to type in box 1, y equals the sine of theta divided by 2. And then in box 2, I'm going to type in 1/2, y equals 1/2. And notice that there are only 2 intersection points between the blue line and the red curve. And if I tap on those, notice I have a solution with an x coordinate of pi over 3, and then over here, 5 pi over 3. Okay. All right, next example. Looks pretty similar to the previous equation. The equation is now sine of theta over 2 equals negative 1/2. Okay, and I'm back to solving it for 0 to 360 degrees. So I'm in terms of degrees now. Okay, so treat theta over 2 like x. Okay, and since sine is equal to a negative number here, that tells me that x is in quadrants 3 or 4. Okay. So if we reason these out, we would be using a 30-degree reference angle in quadrants 3 and 4. So that means x could be 210 or 330 degrees. Okay, so now bring into play that x is really equal to theta over 2. Set theta over 2 to 210, set it equal to 330. Now if you solve those for theta, you'll end up with 420 degrees, and you'll end up with 660 degrees. Okay. Notice that neither of those solutions are in the interval we're trying to solve over. Okay. They're not in the interval from 0 to 360. So that means there is no solution over this interval. Okay, and we can verify this. I can go back and I'll just use the same graph as before, except now I've got to change this to y equals -1/2. Okay, and I'm in radians right now, but that shouldn't matter. Notice that over the interval 0 to 2 pi, which matches 0 to 360 degrees, see how there's no intersection between the two curves. That's why we're saying no solution. Okay. All right, in our final example, we're trying to solve over the interval 0 to 2 pi. The equation sine of 3x plus pi over 18 is equal to 1. So notice that equation has a very sophisticated argument right here. Okay, and I'm going to treat that argument for a moment as though it's equal to theta. Okay, so I'm solving a very basic equation of sine of theta equals 1 to start. That's going to lead me to a quadrantal. Okay. On the unit circle, I'd be placed at 0, 1 for sine to equal a value of 1. And that would mean we're working with a solution of pi over 2. Okay, so now we bring into play the fact that theta is really equal to 3x plus pi over 18 in this equation. Okay, so I'm going to set that argument equal to pi over 2 and solve for x. All right, so to do that, I'll begin by subtracting pi over 18 from both sides. That's going to require you to get a common denominator. All right, so the pi over 2, you're going to have to think of that as, let's see, 9 pi over 18. Subtracting that by pi over 18, you'll end up with 8 pi over 18, which reduces to 4 pi over 9. And then you're going to divide both sides by 3, or I think it's more helpful to multiply by 1/3 in this case. And that'll give me x equal 4 pi over 27, which is definitely within the interval 0 to 2 pi. Okay. All right, so now we want to get a coterminal angle to pi over 2 in the positive direction. To see if we're going to get more solutions that fit within the interval 0 to 2 pi. So I'm going to take 3x plus pi over 18. I'm going to set that equal to pi over 2 plus 2 pi, or 3x plus pi over 18 is equal to 5 pi over 2, right? 5 pi over 2 is coterminal to pi over 2. So now I'll subtract pi over 18 over 5 pi over 2 minus pi over 18. That'll lead you to 22 pi over 9 after you get a common denominator and reduce. Multiply both sides by 1/3. That'll give you 22 pi over 27, which is still between 0 and 2 pi. So that's going to be a second solution. Okay. All right, so let's keep going. Let's consider one more revolution. to get another coterminal angle to pi over 2. So I'll take 3x plus pi over 18. And there's two ways you can look at this. You can take that original angle of pi over 2 and you can add now 4 pi to it. So it's like you're adding 2 revolutions. Or you could have taken the 5 pi over 2 coterminal angle and add 2 pi to that. So either way, you should end up with pi over 2 plus the 4 pi is 9 pi over 2. Then you'll subtract pi over 18, get a common denominator and reduce. That'll leave you to 3x equals 40 pi over 9. Multiply both sides by 1/3. You'll end up with 40 pi over 27. Okay, which is also in the interval 0 to 2 pi. All right, now I'm noticing a pattern emerging with my solution. So notice the first solution was 4 pi over 27. The next is 22 pi over 27. See how the numerators are 18 pi apart from one another. And then from the second solution to the third solution, 22 pi and 40 pi, they're also 18 pi apart from one another. So it stands to reason that if I go through this process one more time, I'll end up with a solution of 58 pi over 27. And 58 pi over 27 is just outside the interval from 0 to 2 pi. So I would not include that in my solution set. Okay. All right, let's just for good measure verify all of this using Desmos. All right, so make sure you're in radians. Change that x-axis from 0 to 2 pi again. Type in your first equation. Let's say it's y equals the sine of 3x plus pi over 18. And then for the second equation, type in just y equals 1. Okay. And noticing I have 3 solutions over the interval 0 to 2 pi. So the first solution is at 0.465, which, let's see, if we were to approximate 4 pi over 27, would that give us that value? Sure would. Okay. So noticing same approximation right there. And then the second would be at 2.56, which should be the approximation for 22 pi over 27. Sure is. And then I think you'd find 4.654, that's going to be the approximation for 40 pi over 27. Let's just check that. Sure is. Okay.